Hi, everyone. My name is Robert Makoviak, and I'm an outbound product manager in Oracle's database development organization. In this presentation, I'll be discussing some of the new features of the upcoming Oracle Database 23C that simplify distributed, event-driven, and microservices application development. This is Oracle's usual safe harbor statement, reminding you that this material covers Oracle's general product direction and is intended for informational purposes only. Because this information may change, should not be relied upon in making purchase decisions. Okay, every new version of the Oracle database builds upon the previous release. So keep in mind that Oracle Database 23C is the sum of the functionality in the 21C innovation release, plus all the new features, enhancements, and bug fixes in the 23C long-term support release. Some of the functionality discussed today first appeared in Oracle Database 21C, and that'll be pointed out where appropriate. If you're interested in more details of features introduced in Oracle Database 21C, just scan the QR code at the bottom left of this slide. And if you look at the key focus areas listed in the bottom right, I'll be focusing on microservices and developer productivity, highlighted in red, for this presentation. But other areas like JSON, graph, security, and more will be covered in other presentations in this series. Modern application development uses a whole new generation of data technologies and application architectures. In addition to relational data, we also have data stored as documents in JSON and XML, spatial data, graph, and text. And in addition to traditional data warehouses, we now also have new types of analytics like machine learning or graph and lakehouses. And workloads have evolved from monolithic type applications to also include microservices, geo-distributed applications, Internet of Things, blockchain, and more. For developers, developing applications has gotten more complex since more technologies may be involved than in the past. One approach is to use specialized single-purpose databases for each required technology, but this can further complicate application development by requiring developers to go beyond core application functionality to develop the plumbing required to integrate all these mixes of technologies into a coherent form. This integration includes things like maintaining consistent security, availability, performance, recovery, data consistency, and filling in functionality gaps across the various technology components. So in Oracle Database 23C, we focused on making it easier for developers to build next generation of data-driven applications, regardless of the development approach, while maintaining the same levels of performance, availability, and everything else I just mentioned at any scale, which is exactly what the Oracle database is famous for. So Oracle has spent decades evolving the database to support increasing numbers of data models, workloads, and application development styles, leading all the way up to today's modern applications. And all of this is incorporated into the Oracle database for free, allowing developers to focus on innovation and not integration. So if you want to run a graph or a JSON query against your existing data, you can just add a SQL statement to the application rather than adding an entirely new type of database, migrating your data, and then having to maintain it over time. But this doesn't mean being forced to create monolithic databases. Oracle gives you the choice so you can decide how best to develop your application and how you want to integrate and deploy the various chosen platforms. So for example, you could decide it's best to use Oracle for OLTP, JSON documents, and graph, but use Kafka for microservice messaging. Or maybe something else. The choice is yours. In summary, Oracle's database vision is to make it easy to develop and run modern applications and analytics for all use cases and at any scale. Application architectures have evolved from monolithic to more decentralized and distributed architectures like the ones described on this slide. And Oracle's decentralized database architecture makes it simple to use decentralized application development techniques. If you're not familiar with these concepts, I encourage you to familiarize yourself with the details. But in a nutshell, Microservice applications are designed as loosely coupled services with clearly defined data and functional boundaries rather than as a single monolithic application and database. Sharded databases distribute data sets across multiple physical databases or shards, possibly in different geographic locations, but presented to the application as a single logical database. And with data mesh architectures, data management is distributed based on domain-oriented data ownership and governance rather than in a single centrally managed data source. So next we'll be looking into specific Oracle database features that simplify decentralized application development techniques. So these are the 4 features I'll be covering today. Oracle Database 23C improves the performance of transactional event queues that are key to supporting microservice applications in the database. If you're not aware, transactional event queues first appeared in Oracle Database 21C and are the latest evolution of Oracle Advanced Queuing. Kafka compatibility is also a focus of 23C. Kafka has become an important standard in the industry, and now Oracle Database 23C can be used as a source and target for Kafka applications. The OKafka Java library uses Oracle Database high-performance transactional event queues to allow developers to build Kafka-compatible applications that produce and consume events that are transactionally integrated with data changes in the database. With reservation-based escrow locking, lock-free reservations hold locks on hot data for short intervals of time, improving user experience and concurrency. Transactions reserve an amount from a reservable column value without actually locking the row, and then the locking only happens when the value is modified during a commit of a transaction. And Prometheus Grafana for Oracle, or PGO, provides observability into a wide variety of database metrics geared toward developers. While these features are not limited to microservice-based architectures only, they can radically simplify distributed application development, which is the theme of this session. But it doesn't stop there. In addition to these 4 features, there's plenty of new and existing features, enhancements, and exciting breakthrough technologies for developers in Oracle Database 23C, like JSON relational duality, property graphs, blockchain tables, and best-in-class security features. Over 300 new features overall. So let's take a closer look at the first feature on our list, simple transactional microservices. Decentralized applications are implemented as loosely coupled microservices using asynchronous events to initiate application and cross-microservice actions. For example, publishing a process this new order event can cause multiple microservices or applications to take action in their specific functional areas. These events are published using event platforms like Kafka, and event handlers are usually hand-coded by developers to implement actions, change database state, and produce other events. Ensuring that event handlers preserve data consistency across services is difficult because they have to handle issues like process and network failures, concurrent changes, restores from backup, and disaster failovers. If not handled sufficiently, any of these situations can cause data divergence that tends to snowball into additional divergence over time. Even if we ignore cross-microservice consistency, maintaining consistency between a stateful event platform and a single stateful database is difficult. Most event platforms require developers to hand code consistency and failure recovery into every event handler. For the simple publish and consume case, developers can manually track the state of event consumption and store it in the database. But for more sophisticated cases involving multiple events and database operations, maintaining consistency requires enormous amounts of error-prone work. Oracle and relational databases in general have long addressed the pain point of application-coded consistency by providing ACID transactional support within the database platform itself. If you're unfamiliar with the term ACID, it's an acronym that stands for the transactional properties of atomicity, consistency, isolation, and durability, intended to guarantee data validity despite errors from failures. The benefits of atomic transactions are well understood, but seem to have been de-emphasized in recent years. For example, NoSQL databases initially claimed that transactions were unnecessary and even potentially harmful. But users of NoSQL databases soon learn through experience that coding data consistency into an application is error-prone and time-consuming. And while newer versions of Kafka do now support transactions, it's only within the event platform itself, not between Kafka and databases or across databases. So this is where Oracle provides unique solutions that address these pain points. Oracle Transactional Event Queues, or TxEventQ, are built for high throughput messaging and streaming of events in transactional applications. Oracle Transactional Event Queues is a free event platform built into the Oracle database that's been continuously enhanced for over 20 years. It was previously called Advanced Queuing, or AQ, and is used by tens of thousands of enterprise customers today. Transactional event queues make developing microservices simpler by transactionally integrating database changes and their associated events. This integration provides exactly one semantics and idempotency without complex, error-prone, and inconsistently applied application coding, along with the security, availability, scalability, and all the other benefits of the Oracle database. In fact, Oracle's scale-out architecture can process over 1 million events per second. Here's a simple example illustrating the transactional integration of database data changes and associated events. We have two microservices, one for the customer management application on the left and the other implementing a loyalty program application on the right. The customer management microservice on the left begins a transaction T1, which writes data to the database and then sends event A and commits. By combining the DML and the events as a single atomic unit of work, the database transactionally guarantees delivery of every event A exactly once. Likewise, the loyalty program microservice on the right continues the chain event-driven workflow by beginning a transaction T2, which receives event A, performs some processing, sends event B, and commits in a single atomic transaction. Without these integrated transactional capabilities, it's up to the developer to handle data consistency within the and across microservices. This slide lists a few of the common design patterns used to provide different levels of consistency across microservices, but as you can see, each requires developer effort to code, test, document, and maintain over time. And all this effort can be avoided just by using Oracle Transaction Event Queues, freeing up developers to focus on innovating core functionality of the application. This slide will show the full capabilities of Oracle Transaction Event Queue architecture while adhering to Oracle's database vision of making modern applications and analytics easy to develop and run for all use cases at any scale. Each database instance acts as like a broker with a Kafka-like architecture with topics and partitions, which are implemented in Oracle as queue tables and event streams, and supporting produce, consume, and publish, subscribe data design patterns. As you can see, most application development languages are supported with REST APIs and a command line interface and native Kafka Java clients. You can connect multiple databases together and have messages or events propagate across database instances or brokers. And application consumers can be figured to connect to their nearest database instance, allowing you to really scale out to massive environments. There's also a Kafka connector so that you can join Kafka clusters into the whole event mesh with bidirectional interoperability between Kafka and transactional event queues. Transaction event queues also include a Kafka Java API and Kafka-like REST APIs. So you can use Kafka clients directly against transaction event queues if you want to do that as well. Which brings me to my next topic, Kafka compatibility. One of the new features of Oracle Database 23c is Kafka APIs for transactional event queues. This capability was introduced to bridge the use of Kafka and transaction event queues for event-driven application architectures, and has three main parts. One, the ability for Java applications written using the Kafka API for Java to use the Oracle database as a Kafka broker. Two, the ability for the Oracle database to provide Kafka REST APIs. And three, connectors that allow the bidirectional propagation of events between Kafka and the Oracle database. How is this possible? Well, transaction event queues in Kafka have similar architectures. So when you use transaction event queues with Kafka APIs, the Kafka topics and partitions map directly to transaction event queue partition queue tables and event streams. Developers can build applications using either Kafka APIs or transaction event queue native APIs in order to use the transactional message broker built into the database. Let's go into further detail. Starting with Oracle Database 23c, Kafka apps can transparently use transaction event queues as a message broker by simply switching the broker endpoint. Here's a simple Kafka client application. This is a producer written with the standard Kafka client libraries. Notice the specified Kafka producer library and the Bootstrap server endpoint properties we pass to initialize it. To make this application work with transaction event queues, we only need to make two tiny changes. We change the Kafka producer to the TxEventQ version, which implements the exact same interface, but adds the transactional capabilities we discussed earlier. And we also add the Oracle database address to the Kafka Bootstrap server parameter list. That's all you need to do. The rest of the code is completely unchanged and works as is. So here's a quick demo showing a simple producer consumer originally working with Kafka running against Oracle transaction event queues. The Kafka Java client for transaction event queues, which is available for download in Maven Central, allows existing Java applications using the Kafka Java client to work with transaction event queues after changing the library and broker endpoints from Kafka to transaction event queues. To save time, those two minor changes have already been made to the Java producer and consumer code used in this demo. The producer runs a loop to post 100 messages to the transaction event queue and print to the screen that all the messages have been sent. The consumer then polls for messages for 30 seconds and prints out some information about each message and then closes out. Transaction event queue REST APIs provided in Oracle REST data services are very similar, in many cases identical, to the Confluent Kafka REST APIs. There are many APIs available for functionality like topics, partitions, consumers, consumer groups, offsets, and so on. And here's a quick demo using the transaction event queue REST APIs to connect to a database and run various event queue REST commands, like getting a list of topics, getting the details about a topic, creating a new topic, get the details of the new topic, and create a consumer or a subscriber for the new topic. And other commands. The Transaction Event Queue Kafka REST APIs make it easy to create custom web user interfaces like the example shown here. This example web UI was built using Transaction Event Queue REST APIs and is available online to try for yourself at the link provided on the left-hand side. Oracle Database 23C also supports bidirectional information flow between transaction event queues and Kafka in near real time. Apache Kafka Connect is a framework included in Apache Kafka that integrates Kafka with other systems. And Oracle Transaction Event Queue configures standard Kafka JMS connectors to establish interoperability and complete the data flow between the two messaging systems. So monitoring message transfer across the Kafka sync source connector for transaction event queues can also be done from either side. From the Apache Kafka side, using the Confluent Platform admin check produce consume console for statistics, and from the Oracle Transaction Event Queue monitor system to monitor things like NQ, DQ rates, transaction event queue depth, and database system level statistics, which we're going to cover at the end of this presentation. For more information, there's a list of articles here that you can search for that goes into much greater detail than what we have time for here. Our next topic is a new 23C feature that addresses concurrency and performance in applications with long-running transactions. All right, so what is lock-free reservation? Well, what do applications that provide inventory control, supply chain, banking, stocks, travel, and entertainment have in common? They're all likely to operate on numeric aggregate data. Think of product inventory counts, available hotel rooms, or seats on a plane. These numeric aggregates are generally identified as hot resources because applications continuously read and increment or decrement them concurrently. As such, this requires some mechanism to control the updates to preserve application and data correctness. In conventional locking protocols, execution of concurrent transactions is serialized by locking a row when a transaction begins and then releasing the lock when the transaction completes, either with a commit or a rollback. But this serialization blocks other concurrent transactions from accessing that row until the completion of the transaction that's locked it. In a shopping application, if an end user places an item in a shopping cart and then steps away from the transaction for some period of time, other users could potentially be blocked from buying the same item until the shopper checks out or times out. Or, more relevant to this presentation, a long-running transaction in a microservice application where a resource remains locked for an extended period, potentially making it a hot resource. The long-term resource locking limits concurrency. For example, a microservices application that offers a travel booking service that might need to wait for flight, hotel, and car booking services to complete as part of a long-running transaction. So what's the best way to solve this? Lock-free reservation, also known as escrow locking, improves concurrency for long-running transactions by deferring the row lock acquisition until the actual update. Concurrent transactions acquire a lock-free reservation for the quantity being updated without actually locking the row until the time of commit. Again, the new lock-free reservation feature of the Oracle Database 23c provides an in-database capability that enables concurrent transactions to proceed without being blocked on updates made to reservable columns while maintaining data integrity. In our shopping cart example above, the cart microservice can reserve inventory for an item when the item is put into a shopping cart without preventing other shoppers from purchasing the item. Updates to column values are treated as a lock-free reservation or an intent to change the value in the future while the application or microservice waits for some action to occur in the application workflow. Once the processing completes or an event is triggered, the row containing the reserved value is locked and updated only at the time of commit. Lock-free reservation guarantees that the database honors all reserved updates until quantity exceeds a predefined limit defined within a constraint. To implement this feature, the first thing you need to do is to create or alter a table and define a reservable numeric column, either number, float, or integer, and then optionally create a check constraint for the column to specify conditions for where an update is allowable. If in this example, we create a table with a reservable column called balance and a constraint specifying the minimum balance amount is 50. The optional constraint provides a way for developers to create rules as to when data rows can be updated. Reservable column updates must be either a plus or minus operation, and they don't lock rows, so will not block other transactions from updating the non-reservable column of the same row concurrently. So let's take a look at an example of how all this comes together. In this example, we have an inventory table with the columns item ID, item display name. We have a reservable column called quantity on hand with a check constraint ensuring that there must be 0 or more items in stock, preventing negative quantities. And a shelf capacity column with constraint, making sure that quantity on hand cannot exceed the shelf capacity for that item. 3 rows are inserted for milk, bread, and eggs. And 3 transactions are run concurrently, all against item 1, 2, 3, which is the milk. Transaction T1 updates quantity on hand by -10 for item 1, 2, 3. Next, the modification amount is checked to verify that this request can be reserved. And if all the constraint checks also return true, the request can be placed into the lock-free reservation journal with no row locks yet taken. Remember, these amounts are promised and reserved until the transaction either commits or is rolled back. So instead of this first transaction locking the row and blocking other transactions until it commits, we can now have 2 more transactions take place while the 10 item amount continues to be promised and reserved to transaction 1. Next, T2 adds 20 items to quantity on hand for the same milk item, with the constraint guaranteeing that shelf capacity for milk is not exceeded. And T3 subtracts another 30 milk items from the quantity on hand, all entering lock-free reservations into the reservation journal if constraints allow, so that all amounts are promised and reserved until the transactions eventually commit or roll back. In the final step, the transactions begin their commits. Note that T2, adding inventory, commits first. This transaction might possibly be running from an automated inventory management microservice. The next to commit is T3, followed by T1, which could be from point of sales and online shopping microservice applications. Since no row locks were taken until actual commit time, we don't have to worry about any transactions being held up while other transaction owners go off for a coffee break or another waits for a price check on a different item for that same purchase. In essence, no frustrated users waiting to complete their purchases, all constraint requirements being met, all user quantities being promised and reserved until purchase commits, and most importantly, no complex application logic required to serialize commits in the order that the transactions were submitted. There are some restrictions and guidelines listed on this slide. I'm not going to go through all of these at this time, but some I already mentioned and others are just listed here on this slide. For additional information, simply search Oracle 23C lock-free reservation, and you should find the following articles and document chapters. And lastly, how does Oracle 23C simplify database monitoring for developers? Modern applications, microservices, and DevOps processes are built on containerized architectures like Docker and Kubernetes due to their speed, efficiency, and ease of management. But collecting, aggregating, and correlating database metrics into popular DevOps observability stacks isn't straightforward. Developers have addressed this using Prometheus exporters to aggregate and import data from non-Prometheus data sources like databases into Prometheus, a widely used open source monitoring system and time series database. Prometheus also seamlessly integrates with popular visualization dashboarding tools like Grafana. So based on this architecture, the Transaction Event Queue Monitor System, first available in Oracle Database 21C, consists of these three independent open source components. The Oracle Database Exporter, which is a Prometheus exporter for Oracle Database that collects metrics and formats them into Prometheus-like metrics. Prometheus, a monitor system and time series database which manages metrics collected from the Oracle Database Exporter in time series fashion. And finally, Grafana, an analytics and interactive visualization platform which specifies Prometheus as its data source. Finally, Docker enables this system to operate as a lightweight, portable, self-contained container that can run virtually anywhere. Here's an illustration of the full transactional event queue monitoring system in action. On the left is the Oracle database with the transactional event queues to be monitored. As discussed earlier, transactional event queues are designed for high throughput messaging and event streaming in Kafka-compatible transactional applications using Oracle Database. In the middle, we have the Docker container running the transactional event queue monitoring components. A Prometheus exporter for Oracle Database that connects to the database, queries metrics from GV$ tables, and formats the results into Prometheus-like metrics. Prometheus provides time series database and periodically controls exporter to query, collect, and store metrics. And Grafana, which uses Prometheus as a data source to show the metrics and make them visualized. Grafana is a user interface with charting and computation built in. This whole service is configured, managed, and handled by Docker Compose. To monitor the transaction event queue dashboards using Grafana, perform the following steps. Log into Grafana's dashboard using admin username and password. The welcome page is displayed, and then click Transaction Event Queue Monitor on the welcome page. You can see this where the circle and red arrow is. From there, the metrics are presented in 4 selections. summary across all transaction event queues, database metrics summary, system metrics summary, and subscriber summary for each TxEventQ. So what's new with observability in Oracle Database 23c? Microservice developers typically focus on observability at the application tier. But if what's happening in the database tier is overlooked, developers don't get the full picture of the execution and performance of the full distributed application. Traditionally, Oracle database metrics have been monitored through tools like AWR reports and Enterprise Manager, which are more targeted toward DBAs than developers. So Oracle Database 23c introduces Prometheus Grafana for Oracle, providing database metrics specifically tailored to developers. Developers can now tie in and correlate across Kubernetes container metrics, application tier metrics, and Oracle database metrics, all together in a single unified dashboard. And in addition to metrics, logs and tracing are also enabled to truly get a unified observability picture on a single pane of glass. So expanding on the TxEventQ monitoring architecture we just discussed, Prometheus Grafana for Oracle, or PGO, provides unified observability for developers from the application through the database. PGO uses a framework, open standard components, to address the difficulty developers face in correlating between disparate monitoring, tracing, and logging tools when troubleshooting, tuning, and testing distributed applications. This comprehensive coverage utilizes the popular PLG stack to collect, correlate, and graphically analyze across metrics, logs, and traces, facilitating a unified view of the system within the single pane of glass. Like TxEventQ monitoring, wider database metrics are exported and aggregated into Prometheus. In addition, database logs are collected using the Promtail exporter into Grafana Loki, which is like Prometheus for log data, and Jaeger for distributed chasing. Grafana's strength is the ability to analyze and correlate metrics, logs, and traces within a single pane of glass, which eliminates the need for tedious tasks like matching timestamps from different consoles. The ability to achieve observability across the application tier through the database provides developers with a complete end-to-end perspective of their microservice application architectures. For more information, we've got an Oracle Live Lab on unified observability. There's the unified observability exporters, which can be downloaded and used, and then several blog entries explaining these details in more depth. So that brings me to the end of this presentation. I hope you'll learn some useful information about the new transactional web services capabilities of Oracle Database 23c. Thanks again for attending.